So today we will start some applications of quantum mechanics. So we will mainly be solving the Schrodinger equation, and very soon you will see that we're only using the useful parts and being very practical about it. And the metaphysical part that Professor Pal was talking about in the last lecture, that will slowly recede into the background. On and off, it comes up in many very state-of-the-art experiments, but mostly people have taken it up as a practical tool for solving problems where quantum effects are important. So the first thing we'll start with is the solution for the free particle, which is the natural place to start. However, you will see in many places they start with a particle in an infinite potential well, or particle in a box, because that is simpler to solve. And this free particle requires a lot of philosophy. However, I prefer to start with the free particle so that you can see where the concepts arise, because so far the de Broglie wavelength and other concepts that you have had, the wave packet and matter waves, they all relate to free particles. So I would like to start from there, and then things will get actually simpler as we do the applications later on, like particle in a box, harmonic oscillator, etc. Okay, so it's 10:04. I think I will start the presentation, and hopefully in 2-3 minutes everyone else who wants to join will be here. Okay, I guess you can see my handwritten notes. So the idea is that what we know about a free particle in quantum mechanics is that it has an energy, which is h cross omega, and a momentum, which is h cross k. And this has been very experimentally verified, such as in the Davison-Vermeer experiment. So whatever model we adopt now, using the Schrodinger, for example, the Schrodinger equation, these two things must be fulfilled. So we have some guidelines for the free particle. Okay, on the other hand, for the bound particle, we do not have any such guideline. So what we need to first do is establish that the Schrodinger equation works, and then we can go on to use it for other problems. Okay. So you will find these notes already uploaded, so you don't need to take it down at the moment. So the first thing that I want to point out is that the Schrodinger equation has no derivation. Okay? Right. It has no derivation. It is basically a model for quantum systems. And in the Schrodinger equation, there is the Hamiltonian, which incorporates all the physics of the system. And this is sort of up to you, how you want to design your Hamiltonian. And you need to know about the system, and you need to know how the interactions in the system can be represented by quantum operators. And once you know that, then you can try and solve the differential equation. As you may have heard before, the Schrodinger equation can only be solved for one particle systems, and that which is the hydrogen atom, for example, that you will do, or some of the model systems that we will also do, like harmonic oscillator and particle in one box. So if you go for anything beyond one particle, you will also have to figure out what numerical methods you want to use. Okay? And some analytical, some numerical, all kinds of combinations. And in fact, the whole field of quantum chemistry and a lot of quantum physics is also based on figuring out what approximations are good for solving this equation. Okay.
I wanted to ask, I've seen it said in some places that the Schrodinger equation is a sort of equivalent of Newton's F is equal to ma in quantum mechanics. So, I mean, how accurate is this analogy?
It is accurate, but the problem is that the Schrodinger equation is not deterministic, because it is a quantum picture. But the analogy is correct.
Sorry, your voice became muffled.
Yeah, so the analogy is correct, because just like the F is equal to ma describes the dynamics of a classical system, the time-dependent Schrodinger equation describes how a quantum particle evolves in time. The time-independent one is a bit different. That has no analog in classical mechanics. So you can consider time-dependent one to be an analog of F is equal to ma. There are also actually, you see the classical forces that act on a particle, you have to figure it out before you can solve any equation of motion. So it's the same here. You have to figure out the Hamiltonian yourself, and then you can solve the equation.
Okay.
Yeah. Okay. So then I go back to the presentation. Yeah. Okay. And in quantum systems, there is an additional problem. That is, since psi is an unknown quantity also, it's not just position or velocity as in classical mechanics. You sometimes need to guess the form of psi as well. And then you can find out some unknowns which you put into your psi. So it's more complicated than classical mechanics. Okay, fine. But first things first, let's start with the free particle. So we want the particle to have an energy h cross omega and the momentum to be h cross k. Okay, and we know from de Broglie's equation that a particle in motion, it behaves as a wave. So to guess this function, let's start with functions which we normally use for waves, for wave motion in classical physics. So there are several options. I think you can think of many more, but I will go through 4 possibilities and we will find our correct answer among them. So the first, you can have a sine wave, you can have a cosine wave, you can rewrite them as an exponential of this form, or it can also be like this, where I have just changed the relative sign, just the sign of this. And now we want to guess. So these are all representations for a wave traveling in the plus x direction, and this comes from classical physics wave equations. Okay, and I guess you are also familiar with this expression that e to the power ix is cos x plus I sine x, and e to the power minus ix is cos x minus I sine x, and this is the opposite. Just change the variables here and you get these relations as well. We will use them quite frequently. So if you are not familiar, please look them up before you start studying the rest of the notes. Okay. Now let's go through each of them one by one and see if they will describe a matter wave. So there is something different about a matter wave than an electromagnetic wave, for instance. For one thing, there is the concept of superposition. So for a free particle, if we do not know anything about it, it can be moving either to the left or to the right. So if there is such a particle, then a superposition state wave function should be of the form, say if we are using the sine form, then it is a sine kx minus omega t, which is in the positive direction, and kx plus omega t, which is the wave moving in the left direction. Okay, and by trigonometry we get that it is that it is 2 sine kx cos omega t. However, there is a problem here. Whenever omega t takes any of these values, that is an odd multiple of pi by 2, then the wave function simply becomes 0. So for these values of omega t, the particle would disappear if you consider it as a matter wave. Now this is not possible. So this is so basically, whenever for certain times, for all values of x, psi s is 0. So the particle is nowhere. Now this cannot happen for a particle. Okay, so we have to discard this sign form because it cannot represent a superposition state. The same problem arises for the cos form. Okay, now when we take the exponential form and we take a superposition state in this form, then we can take this e to the power minus I omega t common. Okay, so here I will tell you where I used to get confused. That is this wave traveling left and right. So I found a very nice note online about explaining why a wave traveling to the right is written like this and a wave traveling to the left is written like this. These are basically conventions. You could have done other things. Okay, but why this convention turns out to be the more useful is written in this note. I have also uploaded it on VLearn, so you can look at it if you are also confused like me. They often state it as a very simple, obvious thing, but it wasn't so obvious to me actually. Okay, so you can read about it if you are also confused. Okay, fine. And then if we take e to the power minus I omega t common, then we get this form. Now this is a much better form because whatever the value of omega t here, the wave function does not become 0. So e to the power 0 is 1. So you will always have a wave function. This makes things much better. So this is one possibility for a solution. Now okay. Now for 4, if you also work it out, you will see that it is also valid. Now if there are two possible waveforms, now the question arises, are both true? Can we use both for the same particle? Or is it an either or situation and we have to choose one for a given particle? The answer is that for 3 and 4, you cannot choose both at the same time because there is a problem there. The problem is that if both are true at the same time, then a combination thereof will also be true. So this combination will also be a solution for the matter wave. And in that case, again, we get back to the old problem. So if we take a sum of 3 and 4 as a possible solution, then we again get 2 cos kx minus omega t, which means that the superposition state disappears for some values of omega t. So you have to choose one. And you could have chosen either, but conventionally it is this form, I kx minus omega t, which is chosen as the representation for the wave function. Okay, now we try to motivate the form of the Schrodinger equation. So if this is the wave function for a matter wave, then if I take a derivative with respect to x, I get ik e to the power ikx minus I omega t. And this is psi, and k from the and k is p by h cross. Okay, and so we can say that that p acting on psi, so the momentum operator. So from here we sort of guess the momentum operator. In many cases you will see that people say that the form of the momentum operator or of any quantum operator for that matter, they are generally presented as postulates. But if you just look at the operator h cross I del del x for momentum, it looks nothing like anything, looks nothing like the classical momentum we know. Why should it be of this form? So actually this is sort of a guess from this consideration, that if you take a derivative of the free particle wave function, then you get this equation from where if I want a momentum operator, I can guess that it is h cross by I del del x. Okay, so this is sort of a guess, and we get it from the free particle limit of the because this is the only thing that we know something about. Everything else about all other systems we will find out from the Schrodinger equation and from the operators. Okay. Now, and so let's see what we get from the time derivative. This is from the position derivative. From the time derivative, we get again this form. Okay, and this is basically the time-dependent Schrodinger equation. So when I take a time derivative of psi, I get back the energy. Okay, and this ensures also that my energy of the system is h cross omega, because that is the relation I have used over here. Okay, and if I want then the energy operator similar to the momentum operator, and this is called the Hamiltonian, I get the time-dependent Schrodinger equation. So here I have written it with the E cap to indicate that that is what we start from. Okay. Sorry. I don't know how to turn this. Sorry, I'll just delete it. So this is sort of the motivation. One is you get the momentum operator, and the other is you get the time-dependent Schrodinger equation. Okay. Now we also know something else from classical mechanics, that the energy is related to the momentum by this relation. E is equal. That E is equal to P square by 2m. Okay, and now that we figured out the momentum form, we can find out the operator form in terms of the operator form of the energy operator, or the Hamiltonian, in terms of the momentum operator, and that is this quantity. And this is the operator that you normally see in the Schrodinger equation. Okay. And when we use this operator, so let's see now what the equation we will normally solve is the Schrodinger equation in time-independent form, but we have not come across that yet. So how does that work? So using the energy operator in this form, if I write the equation, I get the Schrodinger equation in the time-independent form. Okay. So the Hamiltonian acting on psi gives me E psi. This is the, and the Hamiltonian operator has this form from coming from the form of the momentum operator. Okay. So this is basically, you see, this is not really a derivation. Okay, so this is just a motivation, and you can just accept it as a postulate, or you can try and understand it in terms of these arguments that I provide here. But none of this is hard and fast. Okay, this is how people guessed what the Hamiltonian will look like and what the form of the momentum operator will look like. Okay, and so the final equation that we get is that the Hamiltonian has, okay, so h psi is equal to minus h cross squared by 2m del square psi del x squared, and this is also equal to the time variation. Okay, and if you put back the psi that we started with in this equation, you will see that this equation is properly satisfied. So that's that for the basic part of the free particle solution. We started with the solution. Note that here we have not solved the Schrodinger equation. We started with the solution from the matter wave picture, and we came to some idea about the Schrodinger equation. Okay. Now we do it in the forward direction. We start with the time-independent Schrodinger equation. Okay, and now knowing the operator for momentum, we write it. We write the equation, and we rearrange the variables. Okay, and since this is a free particle, you can set all energy values to positive. Okay, so any energy, so if the particle is in motion, it has kinetic energy, and all energies are positive. Okay, so we can write this quantity over here as some k squared quantity. And this is a very important relation which we will use many, many times after this. I have written it as K for a particular purpose. So here we do not know that K is the wave vector. But it will turn out that K is the wave vector. So I have written it as K. So but at this point, K is just a constant. Okay. Now for an equation of this form, it is just the equation of a harmonic oscillator in classical physics. And we know that the solutions are of this form. It is A e to the power minus ikx and B e to the power ikx. Okay? And the solution, this is of this form, and K here is a positive quantity. However, if we allow K to be both positive and negative, we can simplify it to A e to the power ikx. But anyway, we will proceed with the more general form here. So I just mentioned this because in some cases you will see that the solution of this equation is given to be in this form. Okay. So and not in the more general form here. But we will write it like this because we want to distinguish between waves traveling left and waves traveling right. But this is the time-independent Schrodinger equation. So this psi is a function only of x, not of time. Sorry, I have written this. This will not be there. Okay, sorry. This is only a function of x. Now we want to find the time part. Okay. And to find the time part, we go to the time-dependent Schrodinger equation.
I have a question okay, so this is some way back when we were arriving at the right expression for psi. So we eliminated 1, 2, 4 and got 3, right? So I was thinking, I mean, typically in partial differential equations, there's a notion of boundary conditions using which you eliminate solutions. So is this actually just boundary conditions which we're applying in an implicit manner? I mean, is that what it is?
Not in this particular case. Here, the idea was that any wave function you choose for a free particle needs to be able to represent a superposition state. So that was the argument. You will see that in some of the solutions we do later, we will use boundary conditions to eliminate wave functions, but not here.
So
actually,
these, yes, sorry.
Yeah, for a free particle, you don't really have any boundary conditions. So that is the problem. If we had, then we could have eliminated even more solutions probably.
So then I don't get it. So I mean, what exactly did we use to eliminate?
It's sort of a guess. So the thing is that for a quantum particle, we need to be able to represent superposition states. So for a free particle, the two possible superposition states are a particle. So if it's traveling in one dimension, you will see I've only used x, then it's only traveling to the left or traveling to the right. There are two possible superposition states. So, but if we guess the sign form for the wave function and we take the left and right wave in that form, then the superposition state becomes a state where the particle disappears sometimes. So that is the problem. So sign form can describe only one, so a deterministic state. It cannot represent the superposition state which is necessary for the quantum picture.
Okay.
Yeah. So it's a bit of a different argument. You normally don't encounter this.
Okay, thank you.
Yeah. Okay. So in the time-dependent form of the Schrodinger equation, we want to now find how it varies with time. We've only solved the x part of it. Here again, we will use tricks which you use to solve partial differential equations. So this is the separation of variable technique. So when you have an equation with a partial differential equation in two or more variables, the first guess that you do to find this solution is to assume that the functional, that these variables are not coupled, that the solution is a product of functions of these different variables. In this case, we have two variables, x and t, and we guess that psi can be a function of x multiplied by a function of t. Okay. Note that here it means that we are only looking for a solution of this form. So there may be other forms which also satisfy this equation. But since we have no clue how to do it, we do the simplest one and see what we get out of it. Okay. So we're only exploring a small subset of solutions. Okay. And then when we apply the Schrodinger equation to equations of this form, so what we're trying to do is we're trying to find out phi. So actually we know phi already from the time independent part. We want to find out chi. That is our goal. So when we apply the time dependent Schrodinger equation to this, we get an equation which is a bit strange in a way, but not so strange since even the first equation started out like that. So on the left we have a function of x only, and on the right we have a function of t only. So we've taken a second derivative here, as you can see. This is with x, so chi t has come out. Over here this is a function of so you're only doing del del t, so phi has come out, and I have moved chi to the right and phi to the left. And the only way in which this can be satisfied for all x and all t is if both sides, if this is actually equal to some constant. And again here, I am calling I don't know why this is happening. Anyway, so actually we are calling this constant E over here, which is the same as the E I've used for energy. Again, at this point, I don't know that it is the energy. It is just some constant. But you will see that it is the energy, so I have used the label E over here. Okay, and in doing this, we actually get two equations out of this. This part equal to a constant, okay, which gives me back the time independent Schrodinger equation, which we have already solved before, and the right hand part equal to E, that gives me the time variation. So I can easily solve this, as you can see. So I integrate both sides and I get ln chi equal to et, and then chi is of this exponential form. So there is a solution. So we have found out phi and we have found out chi, and the product phi chi satisfies the time dependent Schrodinger equation. So there are at least solutions. These solutions are at least valid solutions for the time dependent Schrodinger equation. There may be others. Okay, I find out, but actually everyone has stopped here more or less. I don't know if people try to find other solutions. That is actually an interesting question. You probably should Google it. But these solutions that we have found are actually very important solutions. Okay, and we will see why they are important. So I will list some points here. So the first thing, so look at this equation very, very carefully. What is happening? Okay. So if you look at this equation very carefully, you see that the time part or the form of the time part of the solution doesn't depend on the details of the Hamiltonian. It only contains the energy E. So whatever the details of the system, it does not matter. So basically this time variation part is common to all systems. Okay, this is really a very, very useful thing, which means you don't have to keep solving the time dependent part. You can just tag this factor onto any wave function you find from the time independent Schrodinger equation. Now, the physically observable quantity is the probability density, which is mod psi square. And when you compute this, you see that the psi star, you will have e to the power plus I e t by h cross. So psi star psi, this e to the power, this time factor will cancel out. Okay. So since the probability density turns out to be independent of time. This is again a very powerful statement, because it means that even though my wave function is varying in time, the probability density, which affects all the physical properties, does not change. So we will have constant properties for this system, which is the third point, that all observables, that is expectation values of which are you've seen are computed like this, are also independent of time. And because the properties of the system are independent of time, they are called stationary states. Okay, and these stationary states are very, very important. One more property of the stationary state, which is sort of related to the third point, is that they have a definite energy E. So for the expectation value of, if you have Hamiltonian instead of A, then this is the energy of the system, and this also does not change with time. But also, if you see the value of Hamiltonian squared, the expectation value of Hamiltonian squared, even there you will see that. So why am I computing Hamiltonian squared? Because this will give me the variance of energy. Okay. Okay, I didn't put in the details here. But the point is that the energy basically does not fluctuate with time, and it also does not have a range. So E is always a definite value. It's a single value. Okay, and the variance of E is quantified by the expectation value of the square of the Hamiltonian, and this is also constant, as you can see. Now one more important point which enters here is that the normalization of the wave function, that depends entirely on the time independent part. So it comes entirely from phi. Why is that? So if I take compute psi star psi, then again my time part cancels out, and the normalization condition ends up only being on the spatial part. So this really helps us a lot, which means that the time factor is simply a tag on. You really don't need to think about it once you've done it once. You find out the energies and the spatial parts from the time independent Schrodinger equation, and if you want the time variation of stationary states, you simply tag on this time factor, which is called the phase of the function sometimes. Okay. And then the fifth point. So once we have obtained the stationary states, then we start thinking about a general solution. So what about non-stationary states? So the good thing is that these stationary states, they form a complete set. So they can act as a basis for any general state. So I can take a linear combination of these functions, and I can find a representation for a general state. Okay. So this is a byproduct. And this is because of the beautiful eigenvalue nature of the Schrodinger equation. Because of that, once we have a complete set in terms of the stationary states, we can generate a function for a non-stationary state. Okay. Now, okay. Now let us look at the form of psi a little bit more. So I rewrite this a little bit more. So I've taken k common over here, and I had what did I have here? I had IET, E by H cross, and E by H cross is omega. So I have omega here, and I've taken k common, so I have omega by k here. Okay. Now this waveform also tells me that this is a propagating waveform of a fixed shape. So if you recall, when we studied about wave packets can either have a fixed form and move with some net velocity, which, if you remember, is called the group velocity. And then it can also be a change in waveform, right? So if you just think of waves, you can have a fixed form wave packet moving, or you can have the wave packet moving but changing its shape as it moves. But from the form of psi that we obtained here, we see that it is a fixed form wave packet. So so a free particle in one dimension is a fixed form wave packet. So how do we understand that? So okay, if you just look at this may not be obvious. So we will look at it a bit more closely. So omega by k is defined as the phase velocity. And a phase velocity is basically if you have a superposition of waves traveling in some direction, then each component has its own phase velocity. If they may be the same, for example, if it's electromagnetic radiation, all the phase velocities are c, but they may also be different for, let's say, sound waves or something else. Now, let us think about it a bit more. So this wave is traveling with the phase velocity of Vp. And when it travels, so you think of a wave traveling as particles being displaced at various positions by various amounts. So I am going back to a very mechanical wave picture. It's not really particles moving now, but it's easier to think of it like this. It's the displacement of a point, say a crest point, if it is at x equal to 0, at t equal to 0. So let's say there is a crest at x equal to 0, t equal to 0. Okay? Then, once the wave has traveled for a time t, then this crest will be at x plus vpt. Okay? X plus vt. If the wave is traveling to the right, okay, that is the positive x-axis. Now, also, if the wave is traveling to the left, then this same crest will have been at x minus vpt. Will be at x minus vpt at t equal to t. Okay, and since this is true for all x, not just the crest, it means the shape of the wave is not changing. And where do we get, because these are the terms which occur over here. So I write it as x plus vpt and x minus vpt. So since the wave function has these exact terms over here, you can conclude that the shape of the wave does not change. Okay, and yeah, and I have also mentioned that this is the first term represents the wave traveling to the right, and the second represents waves traveling to the left. Okay, and from here we also identify k as the wave constant. Okay? So once we get psi as this form, then we can see that this is similar to that obtained for a classical wave where k is the wave constant. So that is the argument for identifying the k that we used simply as a constant in our time-independent Schrodinger equation, that it is the wave constant. Okay. So then once we get this solution, we complete our argument that matter waves are basically wave packets. Okay, this is finally conclusive evidence. But there is still a little bit of a paradox. So what is the speed of this particle that is moving? Can we obtain the speed from quantum mechanics? So this is the relation that we had used for the wave constant, that k square is equal to 2me by h cross square. And then energy is, if I rearrange it, h cross k whole square by 2m, h cross k is p, and p is the kinetic energy, half mv square, and p is mv, and when I put it here, I get the energy to be half mv square, which is the kinetic energy. So the energy part is constant, it's fine, it is consistent with what you would expect. So we have not used E as the kinetic energy anywhere while deriving the, while solving the Schrodinger equation, right? But as a byproduct of this expression, we find that E is half mv square. So actually, this is also the point where we identify E as the energy of the system. So we had also not specified what E was before this. I have implicitly been calling it energy, but not really. Okay. And then there is the momentum. Now let's look at this. So classically, the velocity of this particle moving with kinetic energy mv, half mv squared, is root of 2e by m. Now, if we use the phase velocity of this wave, to find out the velocity, then we see that omega is h cross k by 2, and then k is, the phase velocity is omega by k, which is h cross k by 2m, and this is p by 2m, and p is mv, and we end up with half of v classical. Now this is so the phase velocity that we obtain in our wave function solution is not quite the velocity of the particle. So where did we go wrong? So when we find out the velocity from the energy, we are fine, but when we do it from the wave function, we are not fine. What is the problem? The problem lies in the fact that a wave packet which is moving cannot be generated from a single wave. It must be a superposition state. So we did talk about this before when we spoke of wave packets in general, that in order to have a localization of a particle, you need a superposition state. Waves themselves are distributed over infinity. Okay? So, but how do we represent a superposition state from our pure states, so to speak? So the idea is that here, since this is a free particle, there is so the wave constants show continuous distribution. Okay. So then, in order to find a superposition state, we can no longer use a summation. We use an integral over all values of k. Okay, and this is the form. I will not go into a detailed solution of this. For those who are interested, I have also linked some YouTube videos online, but this is not part of your syllabus, so you don't necessarily have to look at it. But I just wanted to tell you how it is done. Just briefly. So
Ma'am, how did we get omega by k is equal to s cross k by 2m?
How did we get this? Okay, just one second. So omega is written as, so it's basically from the wavelength. So omega is 2 pi by lambda, and then lambda is written in terms of the wave constant. Oh, sorry.
Okay,
sorry.
but yeah.
So we don't go to the energy basically. So when we do this, we stick to just wave properties. We don't bring the energy. So omega comes to 2 pi by lambda, and then lambda is related to the momentum, h cross k by.
Oh, okay.
And then you get.
Okay.
So the idea is to just get it from the wave function and not take the energy, because the energy is correct. And then here, okay. So to solve this, basically, what the procedure is that you expand this function k about some localization point k0 at t0. Okay, so when t is 0, so it's like you have some initial wave function and you expand it about some suitable point, like the wave constant of the initial wave function, and then you get a form which looks something like this. This is you don't have to know how to derive it or anything. I just wanted to show it to you, and then what you get is this superposition state where you have e to the power minus x minus vpt whole square, and you have a sort of oscillating phase over here. And from this, actually, if you look at it, you can show that the velocity turns out to be correct. Maybe we do it in the next class, because I didn't manage to complete the notes for that yet. So we will do that in the next class if you are interested, but I think it's okay. So if some of you are interested, you can tell me separately and I will work it out for you. Okay, I just wanted to point it out to you that there is a problem with the phase velocity. So it is not the phase velocity that is the velocity of the particle. Actually, it is the group velocity, which we spoke about again when we spoke about wave packets. But to show that from here is some amount of work, quite a bit of work actually. Okay. So if once you have this waveform, you can show that the group velocity, which is defined as actually d omega dk, that is proper. So that is the velocity of the particle and corresponds to the classical velocity. Also from this waveform, something for those who will work maybe in scattering theory or something later, you will often see that wave packets are approximated by Gaussians. That is also motivated from here, because you see the first component here is a Gaussian. It's common to represent free particles, like particles which are unbounded or scattering off something, as Gaussian wave packets. So this is the thing. Okay. So today was a little bit of a heavy class, so I will not proceed any further now. I will just pause and see if any of you have any questions now. Do you have any questions? No? Okay. So this is basically one of the most conceptually difficult application. All the ones after this will be easier. So please don't get intimidated. Some of you are already familiar, I suppose, especially those doing physics with this. And those doing mathematics will be, I'm sure, not so comfortable with all the little bit of vague derivations that we've done, but much of quantum mechanics is actually based on these sort of ideas. So you intuitively guess things. It's really not the hard and fast derivation all the time. So please don't get very uncomfortable with this.
Sangeeta?
Yeah?
Yeah, I did not follow the entire class. I just kind of joined now and a little bit in the first few minutes. You have mentioned the fact that the free particle, there is continuous energy, there is no quantization. Energies continuously can change, which is the important features that you will have in a particle in a box and so on. But there's a discretization. So that is one important feature. And second is that the wave function is not square integrable.
Oh, yes, I mentioned that. That is true.
So, so I think these are two very important points. I don't know if you have mentioned, so I just thought I will let you know. Okay.
Yes, I did not mention that. That is true, because these wave functions are moved to infinity and there are no boundary conditions, like one of like I think Aditya was mentioning that there are about boundary conditions. So in free particle you don't have really boundary conditions. So if you get it's not possible to integrate them to a finite value. So it's actually infinite.
Yeah. So one easy way to show that it's an exponential Ix is the general solution of the Schrodinger equation. So if you do psi star psi, it is 1. So 1 times dx is infinity, minus infinity to plus infinity. So if you do psi star psi dx,
that is
so psi star psi is e to the power 0. So it becomes an integral of dx between minus infinity to plus infinity, and that is actually infinity. So then psi square is not a square integrable function. So one simple way to show, because exponential Ix is the general solution of the free particle.
Yes. Okay, we showed that here. So if you find the integral, you will see that it is integration of dx is infinity.
Yeah.
Okay. So I will then stop the recording here and